Okay, I will now present my screen. So let me know if it is visible or not. It's enter screen and I will share it. Okay, admit. Okay, someone wants to join the call.
Good evening, sir.
Okay, so is the screen visible? You can see the slide named climate change science. You can see the screen, right? You can see the slide of the climate change science. Recording is done. Okay. Okay. Shall we start? If
Yes, sir.
okay. So um, it will be an interactive session. So I would also like to get feedbacks from you because the lectures and the materials are anyways present in the NPTEL portal. So it will be better to have an interactive session. And just to start, I will go to the presentation. You can see the screen, right?
Sir.
Okay. So yeah. So so I have a few questions just before starting. Now, as the course is named uh, Climate Change Science, I will start with the climate, but just let's get introduced first. I will introduce myself. I am Shubhranshu Vishar. So I am a student, PhD student at the Center for Atmospheric and Oceanic Sciences at the Indian Institute of Science, and I will be taking these weekly sessions um, on Friday from 6 to till our doubts are ended. The typical time is from 6 to 8. So today is the first session for based on the lectures and the materials of the first week. So yes, now the first question at the very first, we would like to get some feedbacks from you. For example, we have seen a lot of cold events this year, especially, and also colder events happen throughout the world in the recent years. For example, in Delhi this time the temperature reached 3 degrees Celsius a few days back, and also at the other parts of India and also other parts of the globe, the temperature is dropped below the normal temperature. So an obvious question would come that is the earth really warming? So we are talking a lot about global warming, but we are seeing the exceptionally cold events. So is it worth saying that the earth is warming? And so I would first like to get opinions from you. What are your opinions about this? The first question, that is, though we are seeing cold events, people are claiming that earth is warming, that is the global warming. So what are your takes on this? Anyone can start interacting. You can
Yes,
just share your
sir.
opinion. Yes,
Good
please.
evening.
Yes.
My name is Zishan Ali Khan.
Okay, okay.
So,
Yes, just
the answer to the question would be that,
right,
uh, for example, you said that in recent times, in the last in few months, we have seen some cold weather events in our country and other parts of the world.
right.
So, I think that these events are short-term events.
Okay,
Their temporal and spatial scale is very. These are at shorter and shorter temporal and spatial scales. So, these cannot be counted in terms of long climatic phenomena, sir.
okay.
So yes, sir.
So what is your idea on defining something long? We will keep on visiting these short-term events because these are related to small variations, as you said, small scale
Uh,
variations, right? So
so
how
when we
should I
talk about
define?
change, so we are mainly concerned about the global climate change. We are
Right,
talking at a large temporal and spatial scales. So when we define climate, it is the aggregate or average of the weather phenomena. So
right,
we cannot say that if the temperature of Delhi is dropping for some years, for a year or two, we cannot say that these indicate that the Earth is not warming. If we will take the average of the whole Earth system, then that will indicate whether Earth is warming or not.
right. So there are two types of these changes. One is local change, another is global change, right? So if you are dealing with the local change, then at some parts the temperature might grow, the temperature might decay at some time, some parts, and depending on different times. But if we take long term average, these basically if we are taking a long term average, then these small scale variations are smoothened out or averaged out by our process of averaging. So we can see an overall change, especially during longer time periods, let's say for 5 years, for 10 years. I mean, the climate is usually defined for 30 or 40 years. So in this time scale, we would be concerned about what is happening. And these variations, which are short term, and also there are different variations, scales of variations also. One is weather, which is from weekly to monthly scale. Another is in climate, I mean just before the climate, so that is, I would say, short time climate change. Another is the large change in the climate. So we need to take the average of a few years and also average over a larger area. So that will decide whether it is changing or not. So thank you for your interaction. And with this, we would come to the second question. Now, there might be changes. I mean, there has always been changes, as you know, from ice age to warmer period when there was very little ice in the earth, and when the earth was also covered in ice, mostly covered in ice. That time we have also, I mean, not we have, but people have experienced, the species have experienced that time. So how to confirm that this warming or this global warming is due to human activities and it is not natural? So it can be due to some other events, for example the variations in different elements of the nature, and variations due to the path, due to the orientation between sun and earth. So how to confirm that it is anthropogenic or human related and not natural? So any ideas on this? Anyone has any ideas that this is due to human activities and not natural? It can be natural also. How should we prove that it is natural or it is not natural like that?
So one way we can confirm that the climate change that is occurring in our world is largely to anthropogenic activities is that uh, we can compare the concentration of carbon dioxide in the atmosphere with the with that of with the concentration prior to the industrial revolution.
Okay,
So this is one way.
okay, that's fine. But how to relate? I mean, that indicates that carbon dioxide is rising. But how to relate that carbon dioxide to the global warming? So, how to make the connection between these two? Two events can go parallel, but they have to be causally connected. So, how to
Sir, we know
perform?
that carbon dioxide is a greenhouse gas. So if the concentration of carbon dioxide increases in the atmosphere, it causes more terrestrial radiation to be trapped in the Earth system. So
Right,
the more the concentration of the carbon dioxide in the atmosphere, the
right,
more will be the global warming and increase in the average global temperature of the Earth. So if the concentration of the carbon dioxide is increasing rapidly, so
right.
it means that it's not natural, it's due to anthropogenic activities.
Okay. Hmm. So as you have mentioned the industrial revolution, so after that a lot of fossil fuel and also a lot of, I mean, we required a lot of energy for growth of the society. That's why we used a lot. I mean, in the past there has the earth has experienced different events in which the carbon dioxide also increased or decreased naturally, but for this time we I mean burned a lot of fossil fuels, and for that reason the carbon dioxide shoot up, and after that I mean the earth is also warming, as you have mentioned that it is a greenhouse gas, but that statement also requires some verification. How to confirm that carbon dioxide is a greenhouse gas? That is the next step that also we need to investigate. So I mean, otherwise, I mean, we know that carbon dioxide is a greenhouse gas, but what is the physics behind that? What is the chemistry behind that? That we also need to look at. Now, yeah, so with this, I would also like to, I mean, I mean, I like to, I mean, just mention one obvious statement that might often come into our mind, that it is only 420 parts per million, 1 million lakhs. So only 420 per 10 lakhs. That is the concentration of the carbon dioxide. That is the relative concentration of the molecule. So is it strong enough to cause global warming? Because in our atmosphere, the oxygen and nitrogen still are the major gases. So that together constitutes almost, I think, 95 to 96% of the atmosphere. So, how can this small amount, only 420 parts per million, cause this entire global warming? That is also of concern. So, I am just trying to relate these questions because some questions might seem very obvious and I mean counterintuitive also, that a small change can, I mean, how it can impact the world a lot, and these questions will come again and again, but as we will go through the course we will understand that this has some implications and there are scientific reasons behind that. Okay, so any take on this? Do you have any views on this? That uh, the carbon dioxide has very small concentration. Still, how can it control the large, I mean, the global scale or the climate of the Earth?
Carbon dioxide is a greenhouse gas, right? So other gases, noble gases like argon and
Right,
nitrogen, not the greenhouse gas.
right,
So I think the carbon dioxide actually backscatters some of the infrared rays that leave the Earth's surface.
Right.
So it will trap some of the radiation, and hence the temperature
Yes.
of the
Yes, I
Earth would
mean,
increase.
basically other gases, especially oxygen and nitrogen, and you also mentioned about argon, which is an inert gas. So these do not absorb in the range of Earth's emission, that is in the infrared region, and the carbon dioxide actively participates in absorbing or trapping that radiation. That's why it is even in the small increase in the amount of carbon dioxide would cause greater increase in the temperature. Another thing I also mention, that is the, I mean, of course, I think as we will proceed in the course, we will do some calculations about the sensitivity of the different gases and also different elements. Sensitivity means if you increase an element by a small amount, how would that impact the temperature or other factors, that is the sensitivity. So changes of something else by some unit change of something which is of concern. So the carbon dioxide has high sensitivity. Methane has higher sensitivity, but methane is still less in amount, but it is also a greenhouse gas. Another thing is that this is this carbon dioxide or methane or the greenhouse gases, they are not present in a particular concentration which is saturating the absorption spectra. So the absorption is still not saturated. So there are gases, if we increase the gases by some amount, they will still absorb more and trap the heat. If they were saturated, or I mean, saturated means whatever they could capture, they have already captured. They won't capture anymore. The case would be different. So one is they have not reached the point of saturation. So if you increase the carbon dioxide or other greenhouse gases, still they will absorb the radiation by some small amount. Okay, someone said that I am not audible. Am I audible? Mm, okay. Okay. Can you confirm whether I am audible or not?
Yes, sir. Audible.
Okay, audible. But just for the question, I am just repeating. I am repeating 2 points. One point is I think someone mentioned that carbon dioxide is a greenhouse gas. Uh, this is mic of, what is that? Someone's mic is unmuted. Can you please mute yourself? Someone's mic is unmuted. It will be better if someone whose mic is unmuted, someone, uh, un, Ankit, Mukesh, can you please mute your mic? It will be better. I think for that. Okay, thank you. Yeah. So I'm just repeating 2 points. One is carbon dioxide is of course greenhouse gas. So is methane. So is nitrous oxide. So is sulfur hexafluoride, SF6. But another point I would like to mention is, if we increase the amount by some value, they will still absorb some of the radiation of coming, which is coming from the Earth's emission. So the atmosphere is not yet saturated for these gases, uh, at least in terms of absorption spectra. If it were saturated, then it would not cause more trapping of the heat. but they are not saturated. I think for planets like Venus, it is mostly composed of carbon dioxide. So it has, of course, reached some equilibrium, which is very bad. It is very hot. I mean, it is the hottest planet in the solar system, but the carbon dioxide is so high in concentration that it has reached the saturation value. But here, as it has not reached the saturation value, it is concerning because after it increases, it will absorb some radiation, and due to that cause, it will trap heat, it will increase the temperature, and the whole humanity and the life on earth will be at risk. That's what I wanted to mention. Any queries? If not, I will go to the next question, but I will stop for a minute or so. Shall I proceed to the next statement?
Yes, sir.
Okay, so for the next statement, I would just like to mention. So let's say the greenhouse gases are causing the problems. So is it better to have no greenhouse gas, or it is better to have more greenhouse gas, or it is better to have a few, I mean, a small amount of greenhouse gas? What are your opinions on this?
Yes, sir. So my opinion, based on my knowledge, is that if there were no greenhouse gas, then the heat budget. We know that the greenhouse gases play an important role in managing and balancing the heat or temperature of the earth. So greenhouse gases are important for maintaining, balancing the heat of the earth system. So if
Okay,
there were no greenhouse gases at all, so it will not be able to maintain the heat of the earth. So it will create some problems like there will be the earth system will become too cold to survive for human beings or for other species of the planet.
right. So now I will just like to have a search in the internet, and I just like to show you something. Let me check. Uh, um, Goldilocks. Have you heard of the Goldilocks zone? Uh, okay, so can you see the picture here? So here, based on the type of the star, they have uh, drawn the zone where um, the planet can be habitable if it is put in that particular region. So I mean, they have defined optimistic habitable zone, conservative habitable zone. So there are many planets. You can see that in the habitable zone. Earth is of course one of them, and we have also discovered many planets in the solar system which are at least in the habitable zone. So for habitable zone, um, that it depends on the distance from the given star which it is orbiting around. It is not a particular point, so it stretches for uh, let's say millions of kilometers away from that particular sun. And in that millions of kilometer zone, if a planet is put somewhere, it can have the temperature in which the radiation budget, as you mentioned, would be satisfied, such that the temperature satisfies the condition for the existence of liquid water. In this context, they have defined the habitable zone of a planet. So Earth is of course in the habitable zone, but that is not the whole story. If there were no greenhouse gases, then someone mentioned that snowball, right? Yeah, Earth will be a slow snowball because the temperatures would be freezing, that is below zero. So uh, that would be a problem of the particular um planet, that is for Earth. So that is the point, that it is not only the uh, presence in the Goldilocks zone. Okay. So without the carbon dioxide, the temperature of Earth would be 255 Kelvin, which is I think minus 18 degrees Celsius or so, which is the freezing temperature. So all the water on Earth would turn into ice, as we have seen the definition of the snowball Earth. So that won't be habitable for us. So that is also a problem. So there should be optimal balance of the greenhouse gas, which is not too high, neither too low, nor too high. So especially there should be temperature difference between the surface and the atmosphere. That would define the greenhouse gas effect. Okay, so yeah, so thank you all for your participation in this question. Then we will just see some corollaries to this questions. Now here we have seen this diagram here. By the way, I'm visible and audible, right? So the screen is visible and I'm audible also. Okay, thank you. Okay, thank you. So okay, so just we were talking that how do you see, I mean, how do you see the temperature variations? Because if you just compare 2 years, for example, if someone sits at year, let's say 1944, he or she will see that temperature is high. After that, if they come to the year 1900 and let's say 78, this point, then they will say that okay, the temperature is little down from that of 1944, so there is no global warming. But if we take an average over some years, let's say it can be for 5 years, it can be for 10 years also, we will find that the trend is increasing, and it is increasing after this industrial revolution, that is after 1850. And from that, carbon dioxide is also increasing, the temperatures are also rapidly increasing, and after the year 1960 it has been remarkable, it is steadily increasing and there is no decrease to that. But we can see the interannual variations of this temperature. One year is warmer, another year is cooler, or vice versa. So after a period of warm events, there would be periods of cold events. We know about the circulations in the different oceans of the world, La Nina, El Nino type of circulations. These can locally control the temperature, and for a short period of time, they can also control the temperature. But we need to take the global temperature, global average temperature, and also over a longer time period to ensure that the Earth is really warming. So that's why this image is very important, because there are interannual variations, but after averaging, they are averaged out, or we can get a clear, smoother graph of the trend in the temperature. And you can visit this site. However, I will upload the slides in the portal, or you will be given a link for that. You can also go and find this. This is a very useful website. A lot of things are given here. The next slide is for the global mean temperature anomaly and uncertainty. Now, the temperature cannot have a very fixed, very decisive or very fixed value. There are related uncertainty to that. These are related to measurement uncertainty and also natural uncertainties. Now, while we cannot confirmly say that one particular year was really due to global warming or maybe global cooling if it exists, we can say that in what range, what is the probability density or what is the probability distribution of the temperatures in that particular region. So here you can see a peak value, which is the mean value of temperature. For example, in 2024 the temperature was almost 1.62 or something close to that than the normal value. And before that, there are also distribution towards the left or right or it, so it can be in that particular range, but we can see that the temperature anomaly is more than one, so that is concerning for us. And there are a lot of years after, especially 2010, which are, I mean, repetitively warmer than the normal temperature. In earlier temperatures, in earlier years, the temperature was less than 1 degree Celsius from the normal value or the average value. This clearly depicts that during the last few years or during the last decade, the temperature has repeatedly increased, and there is no doubt that the earth is warming. They often release some statements. For example, the temperature might be greater than 1 degree Celsius with some probabilistic value, less than 1 degree Celsius with some probabilistic value. They use this probability distribution, but now the probability distribution is shifting towards the right. That means having warmer temperatures or having higher temperatures will have greater values of the probability. So if we take one random year, let's say 2026, this year, it is very probable that this year will be higher than the normal or the average value, let's say from 1815 to 1900 relative to that value. So as we don't exactly know what would be the uh, average temperature, we give some probability distribution and we can find a range in which the values will be situated. So that is just a, mathematical representation for this temperature. Okay, now as at the very beginning we had gone through the question that how to confirm that it is due to normal human activities and not normal, that are not natural. So for that we can see this nice graph. So this is the graph of the temperature of earth through geological time scales. So this is million years before present. 1 million means 10 lakhs or 10 to the power 6 years. So these are very old pictures. These regions are very old, and this is relatively new, and this is the current picture, and they have projected some temperatures after this. Now, if you look at this graph, and many might argue that earth has gone through the warmer period in the historic era, so which had the temperature more than 8 degrees Celsius compared to the recent temperature, 1961 to 1990, that averaged temperature. Then why are we so concerned about the global change? What is so special about it? Because we have experienced warmer periods of time, and there were very little snow, or the sea levels were a lot higher. The question is not, the question is not about the historical time scale. If you see the time scale, these are in million years. This small region is in kilo year. Kilo means 10 to the power 3, that is 1000. And in this small period of 150 years, the temperature has increased rapidly. So that is our concern. that in geological time scales, in very large time scales, temperatures will change. That is due to some bigger causes. That is, have you heard of Milankovitch cycle? So there are tilting of Earth. So Earth's axis is not always in 23.5 degrees. It tilts, the tilt changes, and also the I'd say ellipticity of the orbit that changes, and uh, also they would call it another motion, that is precession of Earth, that is also changing with respect to time. But these are in geological timescales. Due to that, the warmer and cooler period that comes, our change or the anthropogenic change is not due to those geological changes. That is completely due to burning of the fossil fuel, excessive use of that, which otherwise wouldn't be present naturally. So the carbon dioxide, which was released, continuously started accumulating those heats, and within a short time period of 150 years, this has changed the temperature by almost 1.5 degrees. That's the concerning point, not the historical point. So I'm just mentioning this because many might show you this data and argue that Earth was warmer, far warmer than today's time before. So that's why we can deal with that problem using this argument. You can ask for any questions on that. Basically for this slide. Otherwise, I will proceed. Someone wants to add. Okay. Okay. Any queries about this slide? Otherwise, I will proceed. And of course, these are the future projections mentioned here, which show that if we don't take strict measurements, the Earth will even warm up more in a only 100 years of span. It would reach the record value of the all-time high. I mean, I'm telling in terms of geological time scale, it might surpass that value as well. There are probabilities for that. So we need to take serious action um, for that. That is the takeaway from this. Okay, shall I proceed to next slide, or you can ask for any queries?
No, sir.
Yes, please. What is your query?
No question, sir.
Okay, I will proceed. Okay, thank you. Okay. Okay, so just to mention about the greenhouse gas effect. Um, Now, what is the basic cause of the greenhouse gas effect on Earth? Now, for any thermal system, there is a concept of equilibrium. So, we know about the first law of the thermodynamics. If we put some heat into some uh, substance, it will increase its temperature, and the increase will be related to a quantity called specific heat. More the specific heat, less the increase in temperature. Anyways, if you put some heat, that will increase the temperature of that particle, or if we take heat, it will decrease the temperature of that element. Now, in greenhouse effect, Earth has enhanced or increased temperature, that means some heat is trapped into the earth. Okay. Otherwise, what happens is the sun's radiation is coming, the earth is absorbing that radiation in different forms, maybe due to snow that is mostly reflecting, but some are absorbed, due to ocean that is mostly absorbing, some are reflected, and due to this land, vegetation, anthropogenic structures, those things. Anything has some reflectance and some absorbance, this type of quantity. So, if it is absorbing radiation, it cannot take, uh, I mean, keep the heat forever. It has to release that heat. And what it does is, if I apply heat to any substance, it will heat up and it will also start radiating. There is a law called Stephen Boltzmann law. So, which states that the radiation emitted, so E has the unit of power per unit area, that is energy per unit area per unit time. That follows the laws. E equals to sigma T to the power 4. Sigma is called the Stephen's constant. It has a value, and we will deal with that later. And it is proportional to the fourth power of the temperature of that body. So if heat comes and it is radiating something, some heat from that, they will eventually reach a steady state. Steady state means the temperature will not change. What happens is, how, let's say X amount of heat is coming, it is also radiating X amount of heat, and X is equals to sigma T to the power 4. Because if it is reaching the thermal equilibrium, then the temperature change will not happen. As we have seen for the earth, it remained in the steady state for a long time. I mean, if we take this region, it is almost steady, so the temperature is not changing. How it can happen is, whatever is coming, the equal amount, almost equal amount is going out. Now, if the equal amount is not going out, if it is emitting more or absorbing more, then the temperature would change. Then due to the, I mean, the change in temperature time specific heat will be the heat absorbed or heat left from that particular planet. I mean, excess heat absorbed or left from that particular planet. Okay, so that is the concept. So in equilibrium, the heat entered would be equal to the heat emitted, or the heat going outside. That will sustain the temperature. Now, for Earth, the albedo is to 0.3. So that is, if we take the solar radiation to be 100%, then 30% of that is reflected via the clouds, let's say, via the surface or the oceans. After that, 70% is retained. So let's say that 70% is entering into the atmosphere of Earth, or the surface, or reaching the surface of Earth. We can take the surface atmosphere as a combined state. Let's say that is entering the Earth. Now that has to exit. If that doesn't exist, then the temperature will either, if it exists less, then the temperature will be lowered with respect to time. If it emits more, the temperature, if it emits less, then the temperature will go up because it is trapping more. And if it is emitting more, then the temperature will go down because it is releasing heat. Now for the balance, we need to have same amount. So anyways, from the earth, eventually the radiation of 240 watts per meter square will go out, no matter what. Now here we just will forget about the global warming. Let's say that is the situation for the steady state. Now if we apply this simple formula, we will put 240 here in terms of E, because it is the radiation, effective radiation achieved on Earth after this albedo calculation. This will be equal to sigma times T to the power 4. You can do a simple calculation, put the value of sigma, which is 5.67 into 10 to the power minus 8 watts per uh, meter square per Kelvin to the power 4. We will get that value. And um, the surface of the earth emits the radiation of 390 watts per meter square. That is more than the 240 watts per meter square. So surface of Earth is emitting 390 watts per meter square. Then some processes are happening, which is basically absorption of that radiation, as you earlier mentioned. That is the greenhouse gas, due to the greenhouse gas. And the top of the atmosphere is anyways emitting 240 watts per meter square, because that is needed for the balance. Now this difference between surface and the top of the atmosphere, or the radiation that is eventually going out of the earth, is called the greenhouse effect. Now if surface would have emitted 240 watts per meter square, then the simple calculation will also show that the temperature of surface would also be 255 K, 255 Kelvin, which is around minus 18 degrees Celsius. You also mentioned that Earth would be uninhabitable for that case, except for very few organisms. Now the surface temperature is higher, the top of the atmosphere temperature is lower. That is the difference, and that is keeping the surface temperature to be around 288 Kelvin or 15 degrees Celsius. This difference is the greenhouse effect. So yes, we require greenhouse gas, otherwise the earth would be frozen completely, given the setup of the current earth. Yes, I mean, if earth was closer to sun, then the effective temperature of earth might be, let's say, 270 Kelvin or 280 Kelvin. Then the story could have been different, but it is not that. Given the setup, that is the law of the thermodynamics. The effective temperature of earth has to be 255 Kelvin, given the solar radiation. That is the point of the greenhouse gas, and the value of the greenhouse gas here is 150 watts per meter square. Similarly, if we do the similar calculation for Venus, due to that particular configuration of Venus, given the albedo and the solar constant, that is the solar insolation, the radiation emitting outward has to be 200 watts per meter square, no matter what, because it is in equilibrium. I mean, Venus is a very hot planet, the hottest planet on the solar system, but it is in thermal equilibrium. So the temperature, let's say, the temperature, let's say, is 700 degrees Celsius, or let's say 700 Kelvin, whatever it is maintaining that particular temperature. So it is in equilibrium. But in order to maintain that equilibrium, it has to emit 200 watts per meter square from the top of the atmosphere, or which is leaving the planet. Now the story is different at the surface. At the surface, whereas in earth the radiation is only 390 watts per meter square, corresponding, if we just apply the formula, to effective temperature of 288 Kelvin. For Venus, the radiation is extremely high, so it is 1600 and 16,100 watts per meter square. So the greenhouse effect is, the gap between these two temperature is 15,900 watts per meter square. So that is causing the planet to be extremely warm. And why is it happening? It is due to large accumulation of carbon dioxide in the atmosphere of Venus. That is the point. If the temperature was, let's say, the greenhouse effect was less, let's say, um, maybe 380, or like Earth 390 watts per meter square, then the story would have been different. Venus could have been habitable. Of course, other factors are also there, but it is not the case. So the difference between the surface emission and the emission which is actually leaving the planet, which is causing the effective temperature of the planet, are completely different, and that is what causes the greenhouse effect. The difference is known as the greenhouse effect for any planet. If the planet doesn't have any atmosphere, then the temperature of the surface will be equal to the temperature emitting from the planet, because there is nothing to trap, so it will not have anything. For example, in Mars, it has a very thin atmosphere, so the greenhouse gas effect is very low, though it has CO2 as the primary composite element of the atmosphere. the temperature is very low and it is not also warming up. Any queries on this?
Sir, the greenhouse that is available in all planet of solar system.
Uh, yes, you asked about the greenhouse gas can.
Is it available or seen in all planet of solar system?
Oh, you're asking whether greenhouse gas is available on all planets of solar system. As per my knowledge, mm, see, on Venus, the greenhouse gas is there, that is carbon dioxide. On Mercury, there is I don't think there is an atmosphere, so it is completely rocky planet without atmosphere, so there is no gas. In Mars, there is small amount of CO2. In Jupiter and these gas giants, they are mostly composed of hydrogen or associated components which are not greenhouse gases, and in Neptune also. So I don't think there are greenhouse gases present in the all planets of the atmosphere. Just for your query, I'm just, because I don't specifically know, I will just particularly search for the composition of, let's say, Saturn. Let's say atmospheric. Let's see. Uh, Saturn's. Okay. See. That is from European Space Agency. So Saturn is approximately 75% hydrogen and 25% helium. So these are not greenhouse gases. Okay. And traces of other gases like methane. Methane is a greenhouse gas, but it will not be available because it is almost constituting the 100% of atmosphere. So not all planets have the greenhouse gases. However, I would like to share one interesting fact, that is the Saturn's atmosphere in the interior is quite hot due to the extreme pressure of those gases, and some internal heating happens in those planets. That's why they are very hot. I mean, their temperature is far higher than Earth's temperature, and I think at the core the temperature might also be higher than the sun's surface temperature. So uh, does that satisfy your query, Abhishek?
Yes, sir. Yes, sir.
Okay. Yeah, so I don't particularly know about all the planets, but I don't think there are greenhouse gases in all of the planets on solar system. So now the point is that greenhouse gas is required if we want to have a temperature range in the habitable zone. On Earth, if it was, let's say, 255 Kelvin, then as you mentioned, it would be completely frozen, snowball Earth. So the greenhouse gas is required in small amounts, but in other planets, let's say exoplanets, there might be situation where the planet is situated in a position such that it doesn't require that much of greenhouse gas. So due to virtue of the position, it gets enough sunlight to warm up the planet. That might be the condition for other planets. And yeah, that is the fact. Okay, any other queries depending on this slide? If not, I will proceed to the next. Shall I proceed? Okay, I'm assuming that I have to proceed. So there is a question. Uh, with this question, we will also see something. The question is, estimate the greenhouse effect of a planet which has albedo of 75%, solar constant 1600 watts per meter square, and surface temperature of 321 Kelvin. Now, uh, can I somehow hide the answer? Yes. Can anyone try? What is your approach on solving this question? I hope the question is visible. The answer is not, but I would like to have any thoughts, any approach for this question. A planet is there, surface temperature is given, the solar constant means the energy it is receiving from its sun is given, and the albedo means whatever radiation is being reflected before entering the atmosphere you can take for the time being is 75%. And now estimate the greenhouse gas effect or greenhouse effect. Any thoughts will be helpful. Anything.
Basically. So I think that we can equate heat in is equal to heat out. So S0 by 4 into 1 minus alpha is equal to sigma T raised to 4.
Okay. So can you
Then
first?
that will be the temperature of the outer layer of the atmosphere.
Okay. Okay. Right.
Uh,
Correct. Yeah. Whatever you have said is completely correct till now. Then the next step.
then we can find out the surface temperature by no, once again.
Surface temperature is given. So you need to find the radiation from the surface, right?
Okay, so sigma 321 raised to the 4 will be the solar radiation emitted from the surface.
Right. Right.
Then if we subtract the, we subtract the amount of energy emitted from the upper atmosphere and minus the surface, then wouldn't that give?
Right. So basically, as we have mentioned, the difference that is from the energy from the surface, or basically the emission from the surface minus the emission from the atmosphere, or that is basically the radiation which is it is getting from the sun, its sun. Now, one question I would like to ask you. You mentioned about the S0 by 4, right? So why S0 by 4? Why not S0? What is your
So it emits in 4 pi r square. Emission is in 4 pi r square.
and absorption?
So option will be, I think, since the uh, okay, the Earth is tilted, so I think it will be 2 pi. I'm not sure about that.
Okay, okay.
Since the Earth is tilted, right? If it was flat, then I think not flat. No, if the axis of the Earth was normal to the plane, then I think it would be 2 pi r square.
Okay,
But since it is tilted, it'll I am not sure how tilted will work.
okay. See, the point is, let me let me, there's something called paint or something. I don't know. Let me try to draw something. I don't know. It's very difficult to draw here, but I hope you can see the screen, right? The paint. So let's say that is the, my drawing is very bad, but let's say that is the Earth, and that is the radiation which is coming from the sun. Okay. Now, of course, the whole area is 4 pi r square. The area of a sphere is 4 pi r square, but it is not receiving the area of a sphere. It is basically lived in the half. The area of this is 2 pi r square, but there is a catch. This area is having normal incidence of light, right?
Yes.
And this area is
All
very tilted, so it is having it has very high inclination compared to this area, so same as this area. So this is highly inclined. So the inclination, so basically the angle between these are 0 degrees here, and these are 90 degrees here, right? Angle between the incident light and this surface of the earth, right? Now this varies as If it is 90 here, it will have the highest value of the insolation. If it is 0 here, it will have the lowest value of insolation. So you can fit it using a sine theta function, where theta is basically the um, 90 degree minus latitude, or if you can take cos theta, you will just get the value, or sine theta or cos theta. Basically it will vary as cos theta. So that will be helpful. If you just multiply the radiation by cos theta and integrate over all the surface areas, then cos theta d theta, that particular integration will be equal to 1 by 4. I mean, it is 2 pi r square here, but due to this cos theta factor, the cos theta d theta, which will again be integrated, and that will give you another factor of half, that will eventually give the total factor to be 1 by 4 or a0 by 4, as we have seen. Okay, so is it clear, or I shall explain something more? So did you understand the logic of 1 by 4, or at least you will be able to perform at your home whenever you get time?
Yeah.
Yes.
How will it vary if since the Earth's axis is not normal, it's tilted, right? So
See, this region, no, I mean, no, I mean, Earth is tilted, that is fine. Earth is always tilted, that is fine. But even if it is tilted, then this part will be unlit. I mean, 50% of will be lit by the sun,
yeah,
and 50% will not be. You don't need to take account of the tilting value of the Earth. I mean, we are just assuming that is as if sphere, and the sphere is tilted or it is not tilted doesn't matter for this energy calculation. So you don't need to take into account the tilting. The tilting, when it comes, is due to the seasonal variations. When you want to take into account the seasonal variations, that is the tilting argument works. But we are now talking about the mean temperature of Earth. So no seasonal variation or no variation of the energy. Okay, does it clear your doubt?
it's
So that is the constant energy balance that has prevailed for years, and that should be the ideal case that we are looking into. We are not bringing the tilting argument. Tilting brings the seasonality, the summer, the winter, those things. We are just, you can just assume one sphere is rotating around the sun and it is receiving sunlight at different angles, at different uh, latitudes, and for that
oh,
the insolation is becoming different for different regions, and if you just integrate it, you will get the factor of 1 by 4. So you can do the calculation just adding one factor of cos theta, or integrating over the whole region from minus 90 to 90 degrees. You can do the integration in different methods. So is it fine?
yes,
Actually, I mean, in arguments they will just say that the projection of the area, the effective projection of that area of Earth onto a plain paper is 1 by 4 times the area. That's why the factor 1 by 4 is coming. So that is the simplest argument, but I think it is better to do an integration and then find the actual value. Because um, let's say one planet is like a triangle. It doesn't happen in nature, but one planet is, let's say, any non have they have non-uniform shape. So then what will happen? Then we need to do the integration, and the energy balances would be different for this different configuration. That's why it is better to understand in terms of integration, or the basic approach. That's what is required. Yeah, so as coming back to the question, as you have mentioned that S by 4 is there, this factor times what is it? Times that uh, radiation absorbed, because it is 100 minus albedo, so that is 25%. We have got the value, uh, and that should be emitted from the planet due to thermal equilibrium, because it has to maintain its temperature. And that radiation emitted from the surface using the Stefan Boltzmann law, we got sigma T to the power 4 after calculation, which is 602. So the greenhouse gas effect is just the difference between the two. So 602 minus 100 watts per meter square, that is 502 watts per meter square. Okay, so yeah, okay, so okay, I will now proceed to the next slide, which is about Kirchhoff's law. Now there is a law by Kirchhoff, I think Gustav Kirchhoff, is German scientist. So uh, before going into that law, we need to understand what is absorptivity and what is emissivity, because these control the temperatures on Earth, and this is also applicable to any thermodynamical system. So it is very useful, and it is a very general concept. Now absorptivity is how much is absorbed with respect to how much is given. So the energy incident, which is at the denominator, and the numerator has sorry, it is energy absorbed at the particular wavelength and direction. That is numerator, and denominator is energy incident at that wavelength and direction. Okay, so it is the given energy and it is the absorbed energy. The ratio between these two is called the absorptivity. Now in this course, I think for notation for any particular angle, we are using the prime notation above any symbol, and for a particular wavelength lambda, we are using the notation of lambda. So it is applicable for a particular wavelength lambda and a particular direction which is given by prime. Similarly for emissivity, emissivity is a little different from absorptivity, because that is the energy emitted by the system at a given wavelength and direction divided by the energy emitted by a black body, because the black body is considered as an ideal body which can emit the highest radiation at any given wavelength. So it is kind of a perfect body which has emissivity of 1. So the ratio of the energy emitted by the system, I mean of course prime and lambda denotes the wavelength and direction, divided by the energy emitted by the black body for the same condition, for the same wavelength and direction, is called the emissivity. Now Kirchhoff's law states that emissivity and absorptivity should be equal. It is from intuition we can have the feeling of that law. So for that, you can consider one body attached to. Let me go to the paint mode. I don't know whether it will work or not. Let's say there is one body and it is surrounded by black body. So it is our, let's say, element E, and it is the black body at same temperature. It has temperature of T and it also has the temperature of T. Now uh, if they are in thermal equilibrium, then the temperatures will not change. Now for having the temperature change, what we need is that, let's say, the body, of course the body will emit, due to its own property it will emit the energy emitted by the system. So that is the emission by the particular system. It will emit some energy, of course it has some temperature. Why shouldn't it emit? It will emit some energy, and it will also absorb some energy given by the black body. So there is black body is there, it also has temperature T, so it will emit something and it will also absorb something. Now if the emissivity is not equal to the absorptivity, then there would be energy imbalance. Whatever it is not emitting whatever it is emitting, it is absorbing something less or something more, or vice versa. Whatever it is absorbing, it is not emitting the same amount. Then there will be energy imbalance between this body and the surrounding black body. And what happens when there is energy imbalance? The temperatures will not be no longer equal to T for the particular body. It will either increase or decrease. If it gets more energy, it will increase. If it releases some energy, it will decrease. So that's why we mentioned the condition of the thermal equilibrium. If the thermal equilibrium is there, then the absorptivity and the emissivity at a particular wavelength, at a particular angle, that because that is the most general case we are talking about. We will go for further simplifications later on, but that is the most general case, that has to be equal. I mean, these two values have to be equal. Otherwise, thermal equilibrium will start and these two bodies will have different temperatures. Is it clear? Because that is the fundamental concept for this law. You can ask for any queries. Is it clear? Just check question. Okay, nothing. Okay. Okay, but is it clear? So I will go to the next simplification of that. Okay, let's assume that it is fine. Then if there is no angle dependence of reflection or emission of the surface, the surfaces are also named as what, diffuse surfaces. For that, then we just integrate. I mean, the prime is there, so we just integrate over the solid angles, so the prime will go away and alpha lambda will be equal to epsilon lambda. So absorption is equal to absorptivity is equal to emissivity on a particular wavelength, for a particular wavelength. Now the angular dependency is gone. So that we are taking for this course throughout. So this is the basic law. We are integrating over all the solid angles, or let's say the hemispherical solid angles, because we assume that the emission or the absorption is only happening in the forward direction. So that will be applicable. So alpha lambda will be equal to epsilon lambda. Okay. So till this point, is it clear? Because we will be now going to the next simplification. Okay. Okay. So if it is clear, then we will go to the next simplification. That is the simplification is we will integrate over the wavelength lambda. Now it will give us the total emissivity of the surface and the total absorptivity of that surface also. For getting total emissivity, we have integrated from 0 to infinity, that is for all the wavelengths, and we have multiplied the emissivity at each of the wavelength lambda, and we have just put the radiation from a black body, which is E lambda b, at particular temperature, because the temperature of the black body is at Ts, it is emitting at Ts, and we have also divided it by the total radiation that is coming out of the black body, which is basically according to Stephens Boltzmann law. that is sigma Ts to the power 4. So that particular calculation will give us the, you can say it as average emissivity or total emissivity of that particular body. And for total absorptivity, that the calculation is basically the same. We need to uh, apply the absorptivity at each and every wavelength multiplied by the incident light. Now the incident light can be a black body, it can be something else also, but if it is a black body, then we assume that it is a black body at temperature, or it is basically comparable to a black body at a temperature Ti. Then the radiation will be E lambda b Ti at particular wavelength, and the total radiation will be basically the integration from 0 to infinity. But for calculating at, we will be, there's a mistake, there will be alpha lambda for that case, but we can use the epsilon lambda is equal to alpha lambda, this equation. For that it will have that particular value, because alpha lambda is equal to epsilon lambda for this Kirchhoff's law, and that will give us the total emissivity of that particular surface. Now, total emissivity can be different from the total absorptivity, because this source, for emissivity the source, and for absorptivity the source, this can be entirely different. In Earth's case, the source for this absorption is the sun, which is a black body, let's say at 5800 Kelvin. It is radiating at that particular temperature. And for Earth, because Earth is absorbing radiation, um, uh, after that, I mean, after the sunlight comes, it will absorb in some different wavelength region, and that will be related to the emissivity of Earth also. But for that case, the absorptivity will be the integration the from the incident light. So if the sources are same, Ts and this Ti, then emissivity will be basically the average emissivity or the total emissivity will be equal to the total absorptivity. There is no doubt about that. But if the sources are different, for example, one can be sun, one can be earth, or one can be earth, another can be sun. These two values will differ. For earth, if the light is the sunlight, then how much is absorbed by the sun, I mean basically how much is absorbed of the sunlight by the earth is the alpha, and how much earth is emitting is due to its own temperature of, let's say, 288 Kelvin or so. So uh, the absorption in that particular range is affected by the carbon dioxide, greenhouse gases, these elements. But the light which is entering into the earth from the sun, the carbon dioxide doesn't absorb that part of the sunlight, so it doesn't block the sunlight, or let's say it doesn't reduce the intensity of sunlight in that particular region, or which is close to 0.5 micrometer. That is the difference between emissivity and absorptivity when we integrate over all the wavelength values, because one depends on the source of Ts, another depends on the source Ti. That is the difference. So in order to understand the greenhouse effect, we need to understand that thing properly, because a lot of sunlight comes into earth, but a lot of earth's radiation is blocked by these greenhouse gases. Greenhouse gases don't play a role in controlling the incident radiation from the sun. Okay, so any queries on this? If not, I will proceed to the next slide, which is basically is a problem. That is, the temperature of body is 98.3 degrees Fahrenheit, which is 310 Kelvin. uh, what is the energy emitted per unit area of the body? that is a very simple task because we just need to apply Stefan-Boltzmann law. Here we have used the Stefan-Boltzmann law. There is a correction. There should be 5.67 into 10 to the power minus 8 that I need to correct. However, it is the temperature in Kelvin 310 to the power 4. So that is 523.6 watts per meter square. Now, um, that is that is done assuming that Earth is a perfect black. I mean, the body is a perfect black body. Now, if the body is not a perfect black body, and it is having some absorptivity of 0.9, then we need to multiply the factor of 0.9 in front of the sigma t to the power 4. So it will be basically reduced by some factor, and it will be equal to 471.24 watts per meter square. And we can also find the maximum power, the wavelength for maximum power using the Wien's law. So Wien's law is lambda times the temperature is some constant. The value of the constant is 2898 micrometer that we need to put here, and from there we will get the value of the maximum wavelength, which is the peak wavelength of emission, that is 9.35 micrometer, which is also very close to the wavelength in which Earth emits its radiation, mainly in the microwave region. Okay, so any queries on this? Any questions? If not, I will proceed to the next slide. Shall I proceed? Okay, so there I mean, here we are just done a simple derivations of some formula based on the Planck's law. So the Planck's law gives the hemispherical spectral emissivity, that is energy per unit area per unit time, or power per unit area, which is here it is expressed in terms of the frequency nu, and kb is the Boltzmann constant here, h is the Planck's constant. These have specific values, very precise values. C is the speed of light, and we have now converted this equation to the dependence on the wavelength lambda, or E lambda b. We have expressed this in terms of the wavelength lambda. All other factors are basically the same. So just we have used C equals to nu times lambda, that is the um, velocity or the speed of an electromagnetic wave is related to the frequency and the wavelength. Now, in order to derive the Wien's law, we need to differentiate this function with respect to lambda, and from that we will get the equation which has the form x equals to 5 times 1 minus e to the power minus x, and we can't solve it analytically. So we have to solve it using numerical methods, and this gives the value of x. And once the value of x is found, we can just put the other constants here, and we will find that the lambda times t has some value. That value will come to be 2.898 into 10 to the power minus 3, or 2898 micrometer times Kelvin. Okay. Now, okay. Now for Stefan-Boltzmann law, we just need to integrate over the all wavelengths or all frequencies. Anything will work, and that will give us the famous law of sigma t to the power 4. Now, um, some some things we need to keep into our mind, that is a hotter body which is having higher temperature will have lower peak wavelength, so it will emit more in the lower wavelength region. For example, our sun emits in the mostly the in the yellow wavelength region. Now for stars which are having higher temperatures than sun will be shifted towards more green or more blue range of color, so they will emit bluish light from the surface, and which are lower in temperature than our sun, they will emit reddish light compared to our sun. And for this, if you consider this function, this is basically asymmetric, and the left part of the curve has the integration value of 25%, and the right part has the value 75%, because it is steeper in the left and smoother in the right, or gentler in the right. If you take sun's temperature as an example, uh, if we take the value cleverly as 5796 Kelvin, the peak wavelength will be equal to 0.5 micrometer. And if Earth has surface temperature close to, we also choose this value cleverly, it will give you the simple value of the peak wavelength close to 10 micrometer. And that is the reason their emission spectra have very little overlap, so we can treat these two emission spectra differently. That is the benefit of the relatively very tiny overlap between these two spectra. That's why the greenhouse gas which is interfering in the outgoing long wave radiation of Earth will not affect the radiation of incoming radiation from the sun. And there are molecules which can absorb the sunlight, or there are molecules, for example ozone can absorb in the ultraviolet region of sunlight, will have some different spectra. But however, we are very lucky that oxygen and nitrogen, these two major constituents, uh, rarely absorbs any light, so it doesn't absorb basically any of sun's incoming or outgoing radiation. That is a great advantage for these two gases. Otherwise, I mean, this two could impact our Earth very crucially. Any questions on that? Okay. Okay, so I will proceed to the next slide, which is related to, by the way, I must ask you, you have got the assignments right for this first week, right? Have you solved the assignments? Because next few slides will be related to the assignments, so just to guide about the assignments. Okay, anyways, I will just give
No, not solved.
you're you're not sure about the assignments.
We got that, but not solved till now.
Okay, okay. Anyways, I mean, I'm not supposed to discuss the answers of the assignment, but I will just try to guide through that, how to go, if it is helpful. So I will just go through there are two sets. I mean, I think there are 10 problems in the first assignment, and you have a deadline of first week of February or so. That, that you can always check. So I will just go to the problem. There was a question. I mean, this is basically mathematical, nothing specifically related to climate change or the questions to the assignment, but there are given how to calculate the average, which is Very simple. For there are if there are n number of data points, then the average is defined as just add these n numbers and divide it by n. So x bar is summation over I equals to 1 to n xi divided by n. Now this is applicable if the data points are discrete. For example, if the values are different for different I mean they are not continuous basically, so there are distinct gaps between this uh, x-axis, which is here 1 2 3 4 for example. Now for the continuous case, let's say if it varies, let's say there is a variable x of t which varies with t, and we can practically have values at any point in t, and then this method of averaging will not be very useful, because there will always be errors in averaging if we just follow the traditional method. However, we can do uh, the integration for getting the average, which is basically we need to integrate from t1 to t2. Let's say that we want to get the average value between t1 and t2, then we need to integrate from t1 and t2, and we also need to divide by the interval t2 minus t1. So basically it is nothing but the sum, but for the continuous case we have a function defined which is in integration. We need to perform that. Integration is nothing but summation. So that is the process, because there are standard formulas. So if xt has some functional form, then we can just integrate. However, in your case, you are given the assignments which are having discrete values, so just you need to take the um, sum of those values and divide it by the number of cases that you have considered. uh, Another question you will encounter is about the growth rate. So the growth rate from t1 to t2, which will be given by delta x by delta t, is equal to the difference of the value divided by the difference in time. So in delta t time, the value has increased or decreased by delta x. So the growth rate is what is the increase per unit time. That is the logic. So due to that logic, we will just get the value x2 minus x1 by t2 minus t1. That is the growth rate. Now that is applicable for two data points, 1 and 2, t1 and t2. Now if there are multiple data points, then there are ways to find the average growth rate. One way is just to take the average of each step of growth. For example, that is the step from 1 to 2, that is the step from 2 to 3, and that is the last step, which is from n minus 1 to n. Now we can have the average value for each of the steps, and from there we can calculate the average. So we will just add these values, and we will just divide by the number of cases. Now for a better measurement, we can use linear fit. Linear fit is basically, let's say there are a lot of data points, and we want to find a line that mostly um, find that mostly finds the trend of the data point. So let's say there are n data points from x1 to xn. We draw a line which is x equals to at plus b, that varies linearly with t, because the factor a is a constant in front of t, and b is of course in the line equation of line, b is the intercept and a is the slope. And from there, a is basically the growth rate or the change rate. And we can use any programming language for best fit for a few data points, linear best fit basically, because we are given to find the growth rate for, let's say, 10 years or so in assignment problems. And we can just plot those data points, and we can ask the software to find the best linear fit. For Python we can do easily, and for, I think for Excel also there is available methods for getting the linear based fit. But it is better to use, I would encourage you to use open source languages like Python, because it is becoming very popular throughout last 5 to 10 years, and it will uh, be at its popularity in the future also, because it is open source and also very user friendly. Now basically, yeah, just to show that, let's say there are sparse data points from here to there, and these are looking like they are in a straight line, but we need to determine that straight line. For after plotting the straight line, we get the value y equals to mx plus c, and that is the slope of m and intercept of c. And this process is called basically the linear regression, to find a line which has the minimal error, or in terms of distance, which has the calculated or the weighted least distance from all of the data points. I mean, I could have drawn a line from here also, but that will be very odd looking, because it will have a lot of distances from that particular data points. If I could have drawn a line there, that would also create a bigger problem. But this line looks fine, because though it is having points on both sides, mostly it is able to minimize the distance from these points. There is a metric called least square method. That is the metric for determining the straight line. Anyways, you can use any software or programming language to find that. So I would also encourage you, if you get some type of data assignment, you try to do it using any programming language. Okay, be it Python, MATLAB, or anything, Julia, try to do it. Let's see. Okay, so just a small exercise, you can try it, it will uh, be helpful for you. Just to, I mean, if you are finding difficulty in solving any random regression problem, just take a few points like 0, 0.1, 0.2, or whatever, 0, 1, 2, 3, 4, like that, and take any straight line function for y. Let's say y equals to mx plus c. Let's say you can choose m to be 5, c to be 2, or m to be 0.1, c to be 0.3, like that. Now y will naturally become a straight line function of like a straight line. Now you plot that, it will be a straight line. Now you would like to find the best fit if the data is not so organized, because in real world the data is never organized. So data is always I'd say quite noisy, so it deviates from the uh, smooth value, it deviates from the well theoretical values. That's why it is quite random. Now you add small random noises to that, and then you try to plot the graph of x versus y. You will find that that is noisy, and then you fit that using your programming language. Plot y with respect to x and try to fit that. Then you will get the parameter m fit and c fit. If your fit is good, then m fit and c fit will be very close to m and c respectively. Now you can again plot xy using m fit and c fit. That is the values obtained from the software or the programming language after fitting. Okay. Okay. I will just ask for any doubt, and then we will go to the final problem slide. Any doubt on regression or straight line fit? Shall I proceed?
Yes, sir.
Okay, so that will be our last two slides. Uh, there is a question of effective albedo. So, of course, the albedo is defined as the radiation reflected divided by the radiation incident. That is the definition of albedo for any random body. Now, let's say there are two elements P and Q with albedo alpha P and alpha Q, and they have also different areas AP and AQ respectively. So, what would be the effective albedo? Now, if the area of the element P is high, it is having very high area, then mostly the albedo will be controlled by the alpha P. that is for sure, right? If the area of q is less, then alpha q, though it is present, the contribution of that part will be very less. Similarly, if q is higher, then the contribution of this alpha q will be higher and the contribution of p will be less. So we need to wait. We need to put some weights on the albedo. Now, how much of the incident solar radiation will be absorbed by the element P? That is alpha P times SI, because alpha is SR by SI, times the fraction of the area, that is AP by total area. Total area is AP plus AQ. So that factor is there. Now for Q also, that factor will be there, that is the relative factor of the area, and the incident solar radiation is basically SI, the same, and instead of P there will be Q. Okay, now taking together that will be SI. We just take SI outside, and alpha P times this area and alpha Q times this area will be there. Now if we just take the relative areas as Rp and Rq, this will be reduced to alpha P times Rp plus alpha Q times Rq, because we have now divided by the radiation, incident radiation of SI using this formula. Now that will be the fraction of the elements. Now similarly for n elements, if there are n elements, there are n different constituents for a particular planet or particular body, then this will simply be extended from 1 to n and just multiply the relative fraction of the area times the albedo of that particular element. Now we can also verify the example of the planet, that a planet has 70% water with 0.2 albedo, 20% land with albedo 0.3, and 10% ice with albedo 0.8. We just need to multiply the fraction of area, that 70% times 0.2, then fraction of area is 20% times 0.3, and the fraction of area of ice, that is 10% times 0.8. Summing together, or the weighted sum, will give us the albedo is 0.28. So though it is very close to the value of 70% water, but due to the high albedo of ice and land, it has increased a bit from the albedo value of 0.2, and it is mostly close to the value of the albedo of land, the 0.28. For Earth's case, I think the albedo is 0.3, because it is a mixture of ice, water, vegetation, then urbanization, urban area, rural area, desert, many things are there. Okay, so any doubts on this calculation? Because you have a similar question. Of course, the question is more detailed, but the concept is same. So you need to just add the fraction, or you just need to take into account the fraction, multiply the relative area, and then you will find the total albedo for each of the case. Okay, yeah. So please, for any doubts, you may ask questions.
Sir, in this slide, we have seen that the water percentage is and the land percentage are raised. So the albedo is the climate change, one of the significant factor for climate change. So when our water percentage fixed, the rest the surface albedo has any effect on climate change? Major impact it can in upcoming future. Can it play significant role in climate change? The land albedo percentage.
Okay, I got your point. Yeah. So for land albedo, the problem is we are now having a lot of urbanization. Now for urbanization, the roads and the buildings, if the buildings are not reflective and the roads are mostly dark, right, compared to the surrounding regions, and for urbanization there is a introduction of lot of roads, so that will decrease the reflectivity, or that will absorb the radiation more from the surface. So I think if rapid urbanization is ongoing, then that will decrease the albedo, and that will have some effect on the temperature of earth. However, the effect of sea ice is increasingly, I mean excessively high, because the ice has albedo of around 80 to 90%, while the seawater that has albedo of only 10% or so, 10 to 15%. So that change is remarkable. So that is, let's say, 70% change of albedo. So once it starts, let's say due to carbon dioxide, the ice melts, that effect will be lot more compared to the urbanization effect that is ongoing now. That's what I can say. So because that is completely natural and that is also rapid, I mean massive effect. Does that answer your query?
Yes, sir.
Yeah, for detailed calculation, I mean, there are models in which you can change the relative fractions of different setups and see what are the effects. But yeah, I mean, I think global ice, that is the major concern. And we have also heard about the tipping points. If it once goes out of control, then there will be nothing to take it back. It will eventually become ice free. So there is a problem of that also. Now, that is the last slide for today. That is, I just want to show you that Earth's albedo has decreased a lot from the value of 2000 till 2020. And now that is the indication of the increase in CO2. However, that is also another indication for the increase in sea water compared to the or increase in the relative fraction of the seawater, and seawater is becoming ice free. That is the indication of that. That's why the albedo is decreasing. You can see the trend. So the ice is melting. That's why the albedo is decreasing, because ice reflects a lot. That keeps the albedo high. And if now the ice is melting rapidly, this effect is also seen. The reflectivity is decreasing. Now that is the indication. So that is also another parameter that climate is changing, uh, along with the other parameters. There are parameters like sea surface level is rising, of course CO2 is rising, temperature is rising, and sea ice is decreasing. Now the volume of the sea water, that is increasing. These are all indications of climate change, and this is concerning. So, with that, I would like to conclude today's session. But yeah, of course, ask for any doubts. So, you are welcome to ask for. There is a question. There is sorry. There is a chat by. Sir, you can please provide the gist of the things you taught up to, as I am a bit late. Okay, okay, okay. I will. Okay, maybe I will just go through the slides from first to last again, and then I will, for you, I will just mention those things. Uh, Basically, I will not cover this slide because that is just the effect of the albedo we have seen. In this case, in this slide, we have discussed the question that actually related to your assignments, how the effective albedo is dependent on the different albedo and their area fractions. And here we have just explained what is linear fit and how can we fit data points using a linear equation of y equals to mx plus c, and what it means, and what it means by average and rate of change. Now here we have just discussed the Planck's law and Wien's law, and how we can get the Wien's law from the Planck's law, and also Stefan Boltzmann law from Planck's law, just the derivation from this basic equation. From there, we have discussed Kirchhoff's law or Kirchhoff's law, and we have discussed one example. These slides will be provided to you, so don't worry. I will just upload those slides at the particular portal for NPTEL. And here we have defined emissivity, absorptivity, Kirchhoff's law, what is the difference between emissivity, absorptivity, why Earth's emissivity, total emissivity and total absorptivity are different. And just there's just some simple question for greenhouse effect. And yeah, there we have defined greenhouse effect, or basically interacted to see the greenhouse effect. Here we have shown the historical temperature and argued why the temperature anomalies and the temperature rise is significant compared to the historical period now, and why we should be concerned about that. That is not a natural variation. Here just the temperature of the last few years, showing that it is constantly warming compared to the last years. And just this is a very familiar slide that is showing the trend of increasing temperature. And here is the introductory questions that we have discussed. I mean, just we were chatting about some thoughts from you. So yeah, please, any questions you can please ask now. Chat. Now one asks, sir, please explain more about our assignment questions. Okay, so actually the problem is I cannot discuss exactly the assignment questions, but I have explained the methods you would, if you ask anything particular, you can ask, because I have mentioned the general methods for doing your assignment questions. You have two sets of questions. In one set, you have to do, basically you have to do some simple things like averaging and rate of change. So averaging is very simple, just take sum of the values and divide it by n. For rate of change, you have to feed the values linearly, and then you can get the slope of the graph. Here the slope, for example, is m, and the slope will be the rate of change for this case. I think your assignment is for CO2. I cannot explicitly discuss that, but you just plot with respect to time and see whatever change is occurring. This will come as a straight line. Feed the values, get the slope. That will be your answer for the average rate of change. And for effective albedo, you have, I think, different elements like sea, land, and ice. So, and their areas also. So you just weight this with the area. So for example, the albedo is alpha k and the relative area is rk. So these factors you should take into account, and if you sum these, you will get the effective albedo for your particular setup. There are different setups in your questions. So that's all the problem. I will upload the slide, so you will have the methodology there. Anything else? Amrut. Okay, thank you. You're welcome. Okay, thank you for joining also. It was uh, quite inspiring to talk to you all. Just anything you can ask. If you have any questions in general, you can also ask. I will try to answer that also. I mean, related to your course. Any queries you didn't understand, any parts you didn't get properly, you can ask here also. Okay, someone need to record the attendance. Here now it is 11. I think how many, at the peak time, I think at least 20 to, someone has asked a question. Is there any WhatsApp group for this group, or we will assemble in these sessions regularly? So yeah, I mean, there is no WhatsApp group. This Google Meet will work for the uh, next 11 sessions, and we will assemble here at 6 to 8. If you I will also upload the recorded version to the link given in the NPTEL. That will be a YouTube video, and I will of course take some time to prepare that, but that will be uploaded. If you are not able to attend this session, you can of course join, you can of course see the YouTube video, but it is better to join the session in time, because that time is fixed. I will try to join from 6 to 8 each Friday starting from this week. Okay. Okay, you're welcome. Pushkar Arya. Okay, so if there is uh, no question, shall we end the session now? Let me check the recording. Okay, I will just stop the recording then.